Hello everyone. I am Dr. J. Jenny Tajita, Assistant Professor of Mathematics, St. Mary's College, Thuthukudi. My topic is Cayley theorem and its application. First of all, let's see the statement of Cayley's theorem. Cayley's theorem states that every finite group G is isomorphic to a subgroup of the symmetric group Sn, where n is the order of G. In other words, every group can be represented as a collection of permutations. Let's see the importance of Cayley's theorem. It connects abstract algebraic structures to concrete permutation representations, making complex group theory tangible and computable. It provides the theoretical basis for representing any finite group through permutations, enabling powerful computational techniques. Also, it is useful in symmetry analysis in chemistry, physics, and crystallography, transforming abstract mathematics into practical scientific tools. Let's see the sketch of the proof. First of all, what is a permutation? A permutation on a set S. So S should be a non-empty set, is a bijective mapping, that is a mapping which is both on as well as onto. A bijective mapping from S to itself. A symmetric group Sn is the collection of all the permutations on n symbols. Let's see the construction of the proof. Suppose G is a finite group with n elements. We construct a mapping that transforms each element of the group G into a permutation. We define the function fa from G to G by fa of x is equal to a dot x, where dot is the binary operation in the group G for all x belongs to G, where G in G maps to a permutation of G by left multiplication. Clearly, the mapping is injective, ensuring distinct group elements produce distinct permutations. Also, it satisfies the group operation FAB equal to FA composite FB. Therefore, G is isomorphic to a subgroup of Sn. Let's see an application of group theory in chemistry, especially the molecular symmetry. Group theory predicts molecular vibrations, chemical bonding patterns, and spectroscopic properties with remarkable accuracy. Symmetry elements in molecules. Molecules possess various symmetry elements including rotations, reflections, and inversions. These operations form mathematical groups called point groups. For example, the water molecule. The water molecule H2O belongs to the C2V point group. The C2V point group is nothing but which is characterized by identity operation in which it leaves the molecule unchanged. One C2 rotation axis, that is a 180-degree rotation around the principal axis, typically aligned with the Z axis. You can observe the movement of the water molecule in the video. Two vertical mirror planes, the xz plane and the yz plane. In water molecule, the two hydrogen atoms, the oxygen atom and the two hydrogen-oxygen bonds all lie in the same plane, with the C2 axis passing through the oxygen atom and bisecting the HOH angle. We can see the detailed proof of Cayley's theorem. So for each element A in G, we define a mapping FA from E to G by FA of x is equal to AX for all x in G. That is, the image of each x in G is obtained by multiplying x on the left by A. we can see clearly that FA is 1 to 1. Also FA is onto with the pre-image A inverse B. So FA of x is equal to AX and that is equal to B. Thus FA is a permutation on the set of elements of G. Now let G dash is equal to the collection of all FAs where F belongs to G. It actually forms a group of permutations. Since mapping composition is always associative, we need to show that G dash is closed, has an identity and contains inverses. For any FA and FB in G dash, we have the following properties. So FB of x is equal to FAB of x. Thus we can observe that G dash is closed and FE is the identity permutation. Also FA inverse is equal to FA inverse and that is equal to FE. We can observe that FA the whole inverse is equal to FA inverse in G dash. Hence G dash contains identity element and inverses and also it is closed. So it is a group of permutations. It remains to show that G is isomorphic to G dash. Now the mapping pi from G to G dash, which is defined by pi of A is equal to FA, is clearly an isomorphism. It is a one-to-one mapping because pi of A equal to pi of B implies A equal to B, and also it is an isomorphism since pi of A, pi of B is equal to pi of AB for all A comma B belongs to G. We can see a counter example here which follows the proof of Cayley's theorem. Consider the group G equal to 1, I, minus 1 and minus I. The group of permutations G dash can be obtained by the following procedures. So the F1, Fi, F minus 1 and F minus I are defined like this. In more compact form we can write F1 is equal to the permutation 1, F inverse is equal to product of two permutation cycles 1 minus 1, I minus I. Fi is equal to the permutation 1 I minus 1 minus I and F minus I is 1 minus I minus 1 I. So by the proof of Cayley's theorem, G dash is equal to F1, Fi, F minus 1 and F minus I. So there is an isomorphism from G to G dash. Thank you.